In 1881, a Massachusetts zoologist patented a wall-mounted device that converts 80% of sunlight into usable heat, 4 times more efficient than modern solar panels. No electricity, no moving parts, no monthly bill. The average American household spends $1,500 a year on heating. This wall eliminates most of that permanently. It costs $30 to build. It has been proven in university studies and national laboratories, and by the end of this video, you will know exactly how to build one. So why has almost no one heard of it? By the end of this video, you will know exactly how to build this yourself for under $30. No engineering degree, no special tools, just physics that worked in 1881 and still works right now. The answer starts with the zoologist who stumbled onto something the energy industry had no way to sell. Edward Sylvester Morse never set out to change the way Americans heat their homes. Born in Salem, Massachusetts, Morse was a zoologist by training, best known for his work on mollusks and Japanese pottery. Yet in 1881, he filed a patent for a wall that could trap the sun's energy and release it slowly, long after sunset. The idea was almost startling in its simplicity, a sheet of glass mounted just in front of a thick masonry wall. Sunlight pours through the glass during the day, heating the wall behind it. The wall acts like a battery, soaking up that energy and radiating it back into the room as temperatures drop. There are no wires, no motors, no fuel lines, just sunlight, stone, and a pane of glass. Morse described the process in plain terms: collect heat by day, store it in mass, and let it drift out at night. His patent sketches show no pumps, no fans, and no need for outside power. The design was physically complete from the start, not a rough draft waiting for a future engineer to fill in the details. Morse's wall was ready for real buildings, but the question remained: would anyone actually build one, and could it deliver on its promise? The answer first appeared not in America, but half a world away. In 1967, a remote mountain village in the French Pyrenees became the unlikely proving ground for a radical idea. French engineer Félix Trombe, working alongside architect Jacques Michel, built what would become the world's first true Trombe wall at the Odilo Solar Research Station. The setting was unforgiving, with long, frigid winters and clear, biting winds. If a passive solar wall could keep a building warm here, it could work almost anywhere. Trombe's design was no theoretical sketch. He specified a 2-meter-thick concrete wall, painted dark and faced with a sealed sheet of low-iron glass. The air gap behind the glass allowed sunlight to pour in, heat the heavy mass, and trap that warmth until well after sundown. Temperature logs from that first winter showed interior wall surfaces reaching over 120 degrees Celsius, with the wall delivering up to 70% of the building's annual heating needs. For the first time, the concept moved from patent drawings to real architecture, an inhabited building heated by nothing but sunlight and stone. The Odilo wall set a new standard, forcing engineers and architects to take passive solar seriously. But for American builders, the question still lingered. Could these claims stand up to independent, measured testing on this side of the Atlantic? Douglas Kelbaugh arrived at Princeton in the early 1970s with a simple question. Could a wall built for less than the cost of a furnace actually heat a house through a northeast winter? The answer came not from theory, but from 2 full heating seasons in a real home. Kelbaugh's experiment measured every cubic foot of gas burned and every degree of warmth delivered by the wall. The first winter, the Trombe wall cut heating costs by 76% compared to an identical house running only a standard furnace. A year later, after fine-tuning vent placement and sealing minor drafts, the savings climbed even higher, 84% of the heating bill erased by sunlight and concrete alone. These were not laboratory projections or best-case simulations. The numbers came from gas meters and utility statements recorded as the house weathered snow, ice, and gray New Jersey skies. The data settled the debate. A properly built Trombe wall could replace the majority of a home's winter heating needs with no moving parts, no fuel, and no outside power. What made this possible was not luck, but the physics of mass, sunlight, and time, a mechanism as old as stone, waiting to be explained. A Trombe wall works because of thermal lag. the delay between when sunlight hits the wall and when that heat actually reaches the inside of the building. With a wall 12 to 16 inches thick, it takes about 8 to 10 hours for the midday sun to work its way through, so the warmth you collect at noon shows up indoors as temperatures drop after sunset. Glazing on the outside traps the sun's energy, but still lets the light in, creating a greenhouse effect that boosts heat capture. Water stores even more heat per volume than concrete, so some builders use barrels or tanks for extra capacity. The entire process is self-timed by physics, not electronics, no sensors, no timers, just mass and sunlight. This same approach shows up in modern cold climate buildings, like the high-altitude school in Ladakh, India, where Trombe walls keep classrooms warm through sub-zero nights. Innovations like phase change materials and selective absorber coatings have pushed performance even further, but the basic logic remains unchanged. A passive system that works with nature's own schedule. Next, the story turns to the practical details of building one yourself, step by step. Surging oil prices in 1973 sent homeowners and builders scrambling for new ways to cut heating bills. For a few years, passive solar walls like Trombe's seemed poised to become a standard feature in American homes. But when oil prices crashed in 1986, urgency faded. Gas and electricity became cheap again, and the market's appetite for unfamiliar solutions evaporated almost overnight. Building codes continued to favor mechanical systems, furnaces, boilers, certified heat pumps, because they came with predictable ratings and industry-backed warranties. Home builders working on tight margins preferred products that could be installed quickly, inspected easily, and repeated from one house to the next. The Trombe wall, with its site-specific design and lack of moving parts, offered little for manufacturers or service companies to sell. No fuel, no ongoing maintenance, no branded upgrades, just a wall that quietly did its job. Lacking both a clear profit path and a code-approved template, the technology was quietly sidelined, not for failing to work, but because it did not fit the business model. For those still hungry for real savings, the answer became clear. If you want a Trombe wall, you will have to build it yourself. Next, the step-by-step plan that puts this power back in your hands. A buildable plan for solar heating begins with Steve Bayer, a New Mexico builder who believed practical solutions should be within reach. His drumwall design is as straightforward as it is affordable. A single 55-gallon barrel filled with water, placed against the wall, that receives the strongest winter sun, usually the south side, where sunlight lasts at least 4 hours in December and January. The barrel serves as a thermal battery, absorbing heat throughout the day. Behind it, a sheet of plywood or metal-painted matte black draws in sunlight. In front, a clear panel, an old storm window, plexiglass, or greenhouse polycarbonate creates a pocket that traps warmth and shields from cold wind. For under $30, this entry-level Trombe wall prototype delivers measurable solar heat, proving how much energy the sun can provide with the simplest materials. A permanent Trombe wall starts with mass, solid masonry at least 8 to 16 inches thick, built to face true south and catch winter sun for 4 hours or more each day. Concrete block, poured concrete, or brick all serve, but the wall's weight is what stores heat. Double glazing comes next. Old storm windows, insulated glass, or greenhouse panels set 2 to 4 inches from the wall. This air gap is essential. Too little space leads to overheating, and too much, and warmth escapes before the wall absorbs it. Every edge must be sealed with weather stripping or silicone to keep out drafts and moisture. Insulation wraps the sides, back, and especially the top and bottom, using rigid foam or mineral wool rated at least R10, so heat stays where it's needed. The sun-facing surface gets a dark, selective coating, absorbing over 90% of sunlight. Vents, 3 to 6 inches wide, are added only at the masonry stage, placed at the bottom and the top, opening for daytime warmth and closing at night or in summer. For seasonal control, roll-down blinds or exterior shutters block excess sun. A thermometer in the air gap helps fine-tune vent timing. With careful construction, the Trombe wall becomes a steady, low-maintenance source of heat, tuned to the sun's daily rhythm. Before lifting a hammer or stacking a single block, check your local requirements for permits, especially for anything load-bearing. Adding mass to a wall or floor means verifying that your structure can safely carry the extra weight, and in many cases, a quick consultation with a building official or structural engineer is the safest route. Once the wall is up, measure its real performance instead of guessing. Use a simple indoor thermometer or data logger to track how room temperature changes hour by hour, and note when the wall's warmth actually arrives, usually several hours after peak sunlight. Don't expect instant heat. The true test is a steady, comfortable room as the night sets in. For materials, the entry-level test wall can be built for about $30, just a barrel, a black panel, and a scrap of clear glazing. A small frame drum wall, using 2 or 3 barrels and basic lumber, stays low cost and within reach for most DIYers. Full masonry builds cost more, but even at several $100s, they remain a fraction of the price of a furnace or heat pump upgrade. The best approach is simple: start small, watch the numbers, and only scale up once you see the results for yourself. The physics haven't changed since 1881, only the incentives have. Now you know both. If you want more fact-driven, practical solutions for your home, subscribe for the next DIY breakthrough.